Okay, so now we've talked about kinetics. We'll talk about what happens when you create something called an equilibrium. So an equilibrium happens some of the time, not all the time, because some of the time reactions go entirely to completion, meaning all of your reactants are used up, you get 100% products according to the stoichiometry. It all works out. And a lot of reactions work that way, but sometimes there are these weird ones where they don't use up all the reactants. It just kind of sort of stalls. And they set up what's called an equilibrium. And when a system is at equilibrium, it is a balance. I want you to think of it as a very fine balance between the reactants and the products. It's kind of like a seesaw, and we'll talk a little bit about that. And what the definition of equilibrium is when the rate that the reactants turn into the products happens at the same rate as the products turn back into reactants. In other words, you have a reversible reaction. We've talked about those before. And what happens is this reactant turns into a product, and the product turns back into a reactant. And you kind of get this vicious circle going where the net amounts of reactants and products never really change. They don't get used all the way up. They keep the reactants turned into the products. You think, oh yay, it's getting used up, and then the products get turned back into the reactants. Like, well, wait a minute, now I got more, right? And so that's what an equilibrium is. But the definition of the equilibrium is when the rate in the forward reaction equals the rate in reverse. The molecules are constantly in motion. I mean, it's not like it stops. It just kind of stops changing how much. I might have 5 of these and 8 of those. And when one of these changes and one of these changes, I still have 5 and I still have 8. So the amounts of them don't change, but they're constantly trading places. So in an equilibrium system, the reaction in the forward direction reacts at the same speed as the one in the reverse. And they use this thing called the double arrow, used to indicate the system in equilibrium. And what it means is the reactants turn into the products at the same rate as the products turn back into the reactants. And it is a very sensitive balance between the reactants and products, and what you can do is you can shift it a little bit. It kind of plays with it. It moves around a little bit. And so equilibrium systems respond to changes in their environment or their stresses by shifting in the direction of the reaction to accommodate the stress. It's called Le Chatelier's principle. And what it is if you have a change in the conditions, a stress, is you put it on a system which is at equilibrium, the equilibrium is going to shift to reduce the stress and reach equilibrium again. Well, what things can you do to stress them out? Well, you can change the pressure. This only applies to things that are gases. Solids and liquids aren't really affected by pressure. You can change the concentration of the reactants or products. You can change the temperature, or you can add a catalyst, but we really don't talk about that much because it doesn't do a whole lot. All of these stress factors that are here shift the reaction in order to establish the balance. And what does shift mean? Well, shift means that the reaction goes predominantly in one direction to reestablish the balance. Once it gets balanced, it goes equally in both directions. But in order to get there, it has to go in one direction primarily, just for a little bit, temporarily, until it gets itself balanced out again. Okay? If the equilibrium shifts to the left, what that means is the reactants and products, it means it's going this way a lot more than it's going that way. And so the amount of the reactants are going to increase because I'm making lots of them, and the products are going to decrease. If it shifts to the right, what that means is it's going predominantly in this direction and very little backwards. So the amount of products are going to increase and the reactants are going to decrease. So let's talk about these stresses. If you change the pressure, it only affects reactions with gases in them. If you increase the pressure by decreasing the volume, it's going to cause the reaction to shift to the side with the least number of moles of gas. So here's where you're going to count coefficients. Decreasing the pressure has the opposite effect. It goes to the side with more moles. You're again count coefficients. So let me give you an example. This is a gas and this is a gas. I'm actually going to do this demo for you, not with changing the pressure though. But anyhow, there are two gases, and if I increase the pressure on this, on the system, I take the whole thing, they're all balanced, and I squish them, it's going to shift to the side with the least number of moles. So on my left side, I have 1 mole. On my right side, I have 2 moles. It's going to shift left, and literally that's what you're right. Shifts left. If you decrease the pressure, it's going to do the other side. It's going to go more moles. So I have 1 on the left, 2 on the right. It's going to go to the right. And that's all really, that is what you really need to figure out, is which direction is going to shift. That is the big trick for doing these. Changing the concentration is a little tricky. So I want you to think of this as a seesaw between my reactants and my products, perfectly balanced when it's at equilibrium. Okay? If I add an equilibrium a reactant, what it's going to do, this is like a seesaw, you know, me and my identical twin, and I pick up a rock. Well, it gets heavier on this side. In order to rebalance, it's going to have to shift to the right to rebalance itself. If I add a product, again, reactants go to products, perfectly balanced. If I add this, it's like my identical twin picking up the rock. It makes it heavier on this side. To rebalance, it's going to shift left. Okay. If I remove a reactant, again, we have a balance seesaw. If I take away some reactant, it's going to make it lighter on this side. This would be like me and my identical twin and my leg falls off. Okay, it gets lighter on this side. To rebalance, it's going to shift left. And the last one, removing product, again, perfectly balanced. If I take away product, this is where my identical twin, her leg falls off. In order to rebalance, it's going to shift right. Changing temperature is a little tricky because it talks about adding and removing heat. So if you decrease the temperature, you're removing heat. If it's an endothermic reaction, the shift goes left to more reactants. If it's exothermic, it goes right. Increasing temperature does the exact opposite for both. Endothermic will go to the right, and exothermic will go to the left. Better to see it like this. Again, I want you to think of it as a perfectly balanced seesaw. Okay? If I increase temperature, here is temperature. Temperature is my reactant. So if I increase it, my reactant side is getting heavier. To rebalance, it's going to shift to the right. If I have it balanced, and I take away the heat, the reactant side gets lighter. To rebalance, it's going to shift left. Okay, so you just kind of have to pay attention. I want you to think of heat as just another one of those guys, another one of the chemicals. Adding a catalyst doesn't do a whole lot. It speeds up a reaction, but it really doesn't affect how it shifts one way or the other. So, sample problem. All we're talking about is shifting. Okay, if I add more chlorine, this side gets heavier. To rebalance, it's going to shift left. I'll come back to B. If I increase temperature, what's going to happen is my left side is going to get heavy. To rebalance, it's going to shift right. And if I take away some PLC, the PLC side is going to get lighter. So to rebalance it, it's going to go to the right. So those three, not B, you can use the seesaw idea. And just think about it as weight on a seesaw. Okay? And how it rebalances itself. That's all it is. How it's perfectly balanced. And something happens, upsets the balance. How does it rebalance itself? Increasing pressure goes to the side with less moles, not the seesaw. So if I look at this, I have 1 mole over here, and I have 1 plus 1 over here. It's going to go left. Okay? So another example is here where it's a chart. Again, all I'm going to do is I'm going to fill out this part first because this is the most important thing, figuring out which way the equilibrium shifts. So I have my balance. Increasing nitrogen makes that side too heavy, so it's going to shift to the right. If I take away the hydrogen, this side gets too light. To rebalance, it's going to shift left. If I add NH3, the NH3 gets too heavy, it's going to shift left. If I increase temperature, the heat is on this side, gets too heavy, it's going to shift left. Increasing volume is the same thing as decreasing pressure, which means it goes to the side with more moles. On the left, I see 4, and on the right, I see 2, so it's going to go left. Catalysts don't do anything. This right here is the most important thing to be able to figure out, is which direction the equilibrium is going to shift. So to do the nitrogen and the NH3, what you have to do is look at it. Whichever direction the shift is, it's going to primarily react in that direction. The shift direction will increase those compounds, substances, whatever you want to call it. So if I'm shifting to the right, these guys, NH3 is going to increase. If I'm shifting to the left, these two are going to increase, and NH3 is going to decrease. And these are going to be true for all of them, all the way down. But the big trick is figuring out that.